Ross. I am the Energy Process Group Program Manager here at General Atomics, covering hydrogen, renewable, and clean energy processes. The sulfur iodine process is a three-step thermochemical process. It takes high temperature heat in and splits water into hydrogen and oxygen. The first step involves reacting SO2, iodine, and water to create two different acids, a sulfuric acid and a hydriatic acid. In our process, those two acids are in two immiscible phases, so they just separate. We take the hydriatic acid, break that apart into hydrogen and iodine. The iodine gets recycled. We've got our hydrogen product. The sulfuric acid gets decomposed to SO2, water, and oxygen. The oxygen gets taken off, and then the SO2 and water get sent back around for recycling. It's a closed-loop cycle, so that the only thing we put in is heat and water, and we get the hydrogen and oxygen off with all the other chemicals circling around in the loop. The materials challenges for this process are extreme. In particular, the water-iodine hydriatic acid mixture, which is termed HIX because it's a combination of all these different materials together, is exceedingly corrosive. It will eat through basically all of the corrosion-resistant materials. Gold, titanium, Monel, Hastelloy, specialty Hastelloys. So we were left with the challenge of finding materials that basically will just survive the environment of these chemicals, and then seeing if those materials are appropriate for our process conditions. Our process conditions are, again, the corrosive chemicals, high temperature, and pressures up to 20 or 30 bar, 20 or 30 atmospheres of pressure. So we had to find something that was going to work. Glass was out, plastic was out. Glass-lined steel for the low temperature applications on our side was out. So we identified tantalum as the leading material of choice for our application. And we first did explore solid tantalum fittings, but the price and the machining costs of solid tantalum fittings was prohibited. We were looking at $1,000 to $1,500 per fitting for a quarter-inch swage lock type piece, and the project budget just didn't support that, as well as the availability and the capabilities for them to be machined were limited. Basically, it came down to we had to find some way to have a corrosion-resistant fitting that wasn't solid tantalum. Really, the Tantaline surface treatment on standard swage lock fittings for us was the enabling technology. So we used the Tantaline surface treatment on standard swage lock fittings. Basically, the majority of our fittings are a wide range of quarter-inch fittings and half-inch fittings, unions, T's, NPT adapters, a whole slew of fittings. We also have a specialty application for the swage lock ball valve, their half-inch ball valve, which needed some sort of treatment internally to be able to withstand the conditions, as well as be able to hold up to the abrasion of that actuation of the valve. The Tantaline process we use on 90% of our fittings and 99% of our valves. Our 450-degree reactor, actually those process chemicals, since there's no liquid in that area, we can go with a specialty Hastelloy. But as soon as you're away from that reactor, literally the connections from that point, from the reactor on, in both directions are all Tantaline surface treatment. So it certainly enabled us to move from the glass benchtop to industrial type conditions, which is a huge improvement for our demonstration. So it's clearly a molecular bond and molecular treatment to the surface that's allowing it to perform so well. We have data on other materials in these process conditions, and they fail anywhere between 5 minutes and 50 hours, whereas we have the Tantaline process coated parts, the valves and the fittings, that have been exposed to chemical and cycled in process temperature for 9 to 12 months now. So certainly, we tried every other option out there, and they all failed prematurely. We haven't been gentle on our fittings and our system. It's an abusive environment chemically, mechanically, as well. So its ability to withstand the chemicals and the mechanical abrasion has been key to our success. Even though it's an additional treatment cost for the standard swage lock fittings, it is still basically at almost an order of magnitude less expensive than going with a solid tantalum fitting. So we were able to add the cost of the Tantaline surface treatment to 300 to 500 fittings, and still stay within budget. Where had we tried to, we budgeted it out for solid tantalum, and it just wasn't an option. It was unable to support the program. With stainless or Hastelloy fittings, the fittings fail within days. So there is a high maintenance of replacing fittings and parts, and every time you break into the system, it's an increased hazard to the operator, it's an increased risk of further damage to the system. So the surface treated parts have enabled us to go, there's parts that have been in there for over a year without being touched. So the maintenance on those systems is greatly reduced. They're demonstrated to be able to take the process conditions and the corrosion and maintain their viability. Being able to go to a metal-based system that could take the corrosion greatly increases the safety. That gives us a huge engineering safety margin in that system. So it certainly has led to us able to maintain and improve operator safety while going to more and more extreme conditions. My advice would be get one and try it. You will be surprised at how well it performs.